In the last class, we looked at the analysis of the E and H fields for a wave that is being guided inside a rectangular waveguide. We in particular looked at two modes of propagation. One is the transverse magnetic, the other is the transverse electric. So essentially what we did was we looked at the solution for the longitudinal fields, and from that we calculated the transverse fields, and that is the way we saw. So let us quickly write that down. So the first mode was the transverse magnetic mode. So we should write Tm suffix Mn, because as we discussed, the M and N denote the mode details in much more informative way. The second one is the Te suffix Mn mode. So as you know, in case of Tm, it is the longitudinal magnetic component which is 0, and the longitudinal electric field is non-zero. In the Te, it is the opposite. Ez is 0 while Hz is non-zero. So let us write them down, what we had derived. So in case of Tm, we saw that Ez was something of this kind. And in case of the Tm mode, we used the Ez to find out four other fields which are transverse, that is Ex, Ey, Hx and Hy. So we had derived that Ex is of this form. Times C followed by a cos term. Now I am not going to write the arguments anymore. So I'll just write the argument will always be m pi by a times x, and this will be sine of n pi by b times y. So this is how it will look like. Ey will be this. Sine followed by a cos. Hx will be j omega epsilon. There will be a minus sign over here. Cos followed by a sine. So one thing to note here is that beta is the phase constant of the wave that is being guided along the z direction. Beta is not the phase constant for the wave that is entering the waveguide by being incident on one of its walls, but that is the intrinsic phase constant of the wave, that is omega under root mu epsilon, and that is not equal to beta. So we had proved, we had written in the previous class that essentially there is a factor called h. This h square is equal to omega square mu epsilon minus beta square. So that is the way it is. So as you can see, all of these components, they have a e raised to minus beta z component, which indicates a wave that is traveling along the plus z direction. So this is for Tm. In case of Te, we had seen that the Hz is a very similar form with some constant d cos m pi by ax times cos n pi by b y times e raised to minus j beta z. So that is how it is. Then we had seen that the calculation of the transverse fields in case of TE is slightly more tricky. So we had directly substituted the longer form of Hz into those big equations to get the transverse fields and then on those electric fields we had applied the boundary conditions. So again we had got four expressions, Ex, Ey, Hx and Hy, and those are times d. The cos, again I am not writing the arguments, this will be m pi by a, the second will be n pi by b, cos followed by sine times e raised to minus j beta z. Ey is minus j omega mu by h square m pi by a. Now it will be sine followed by a cos times e raised to minus j beta z. Hx is, there will be d also over here, j beta by h square m pi by a d sine followed by cos e raised to minus j beta z, and hy will be j beta by h square n pi by b d cos followed by a sine. This is how it is. So now, of course, all of these big equations, they have their own significance and complexity associated with them. But let's not be boggled by these big equations. Rather, let us try to understand what these equations essentially try to signify. So let us look at what these m and n they indicate. So essentially, in case of the parallel plane waveguide, we had seen that multiple solutions are possible because of different values of m. But now here we have multiple solutions but using two variables m and n. So why I am saying solution? Because I am essentially looking at those points where the boundary conditions are being satisfied with the electric field becoming zero or something of that kind. Now what this m essentially indicates, rather what m and n indicate are the half cycles. So if you recall, the rectangular waveguide looks kind of like this. This is A, this is B. The vertical is the y-axis, the horizontal is the x-axis, while the propagation is along the z direction. So what m indicates is the number of half cycles of the field along the horizontal axis, while n indicates the number of half cycles of the field along the vertical axis. So if let us say m is 1, you will have one half cycle along the horizontal axis. Whereas if n is 2, you will get something of this kind. Now this can be E field, H field, depending on what it is, it's going to be like that. So that is how it is. So this is n is 2 and m is 1. This is an example. So essentially what happens is this m and n, they indicate the number of half cycles of the field in that particular axis, x or y respectively. So therefore every TE or TM mode is characterized with also the m and n values. It is not sufficient to say that okay, it is the TE mode which is there or the TM mode which is there. You have to ask, no, T is fine or Tm is fine, but what is the value of the M and N? That way you will know how the fields are aligned. So what you can see, depending on the values of M or N, there will be distinct solutions for the field. There will be distinct solutions for the fields on the different axes, but there will be infinitely large number of such discrete solutions because M and N can be any natural number. So that is how we look at it. There are countably infinite number of solutions because there are distinct solutions in the forms of these integers M and N which are non-zero. So every value of M or N contribute to some kind of a field pattern, and that constitutes a solution. So every solution you need to specify the M and N values together. So now the question is, what are the possible values M can take? We took an example of M equal to 1, N equal to 2, but we should also ask ourselves, can M or N be 0? So let us check that. But before we check that, there is one more thing you should note. Look at the transverse fields. Look at the transverse fields. What we are essentially interested in is that the wave should be guided along the plus z direction. So if you look at Ex and Hx, in case of Tm, you will notice that there is a cos term here, sin term here, cos term here. So the Ex and Hx components, they are out of phase by 90 degrees. So therefore Ex and Hx don't constitute any wave phenomena. Likewise for Ey and Hy, you have a sin here, cos here, sin here. So therefore there is always a phase difference of pi by 2. Therefore even Ey and Hy don't constitute any wave flow. Likewise for Te. But that should not bother us, because Ex and Hx, they are all along the x direction. So we should not expect them to contribute to wave propagation in the first place. So we know that wave propagation is always contributed by two orthogonal components. So we should look at something like Ex and Hy. So if you look at Ex and Hy, these two are in phase. Likewise, even Ey and Hx are in phase. So therefore, you can have Ex and Hy which contribute to a wave, or even the Ey and Hx which contribute to a wave. You will see something similar for Te also. For example, Ex and Hy, you can see cos, sin, they are in phase. Ey and Hx, sin, cos, they are also in phase. So they essentially are contributing to some kind of a wave which is along the z direction. So this is very important. Now what is happening is that we have to know what are the possible values M and N can take, or rather what are the smallest possible values M and N can take. So let us look at the Tm mode. If either M or N becomes 0 in case of the Tm propagation, you will see that the Ez field essentially dies down because the sign terms become 0. If any of these, that is either M or N becomes 0, that is enough to make that Ez field die down. So if there is no Ez field, these fields will also never exist. So that is why M equal to 0, N not equal to 0, or M not equal to 0 and N equal to 0 not possible. So the minimum values of M and N you need to sustain this propagation is M equal to N equal to 1. That is the minimum needed. Alright. So let us look at the TE mode now. In case of TE, even if M or N becomes 0, even if M or N becomes 0, the HZ field will not die down. It will continue to exist. But if both M and N become 0, while HZ will continue to exist because the cost terms will essentially become 1, you will notice that the other 4 fields will die down because each of them has a sign term. So therefore, M and N both being 0 is not possible. So you can have two cases in case of TE, M equal to 0, N not equal to 0, or M not equal to 0, N is equal to 0. Either of these cases is possible. So you can just work it out. So the minimum possible mode for Tm to propagate is when M and N are 1. So this is called as the Tm11. So the minimum possible mode for TE to propagate is 0, 1 or 1, 0. So this corresponds to TE01 or TE10. So both of these we can call as the minimum, although we shall come back to it shortly. So this is how the way it is. So the minimum values of M and N you need for Tm to propagate is 1, 1. For TE it is 0, 1 or 1, 0. So let's continue our discussion. So now in the previous class we had established something called as the cutoff frequency. So cutoff frequency does not really matter whether it is TE or Tm. It depends on what is the value of M and N only. So the cutoff frequency in case of either would look like this. This is nothing but H. So even here it will be something like this. So this is what the cutoff frequency is. Now let us try to investigate what will be the cutoff frequencies for the minimum possible values of M and N in either of the modes. So we saw that the smallest possible mode that the Tm can sustain is when M is 1 and N is 1. So that is the Tm11 mode. So for Tm11 mode, the Fc will be this times pi by A the whole square plus pi by B the whole square. And in case of the TE01 or the TE10 mode, the cutoff frequency will be something like so. In case of 0, 1, this will become 0 and this will be 1. So let me just write it in the square root form itself, just to maintain the uniformity. And in case of TE10, it will be Fc is equal to 1 by 2 pi times pi by A the whole square under root. So now what we have is, we have 3 cutoff frequencies. What can we say about this? What can we say about this? Which is the smallest? Well, we cannot say which is the smallest at this point of time, although we can say with certainty that definitely it's not going to be this one because it has two sum terms. So now the question is, which one of these two is the smallest? Well, we can say that when we know something about A and B. So what is A and B? A is the horizontal width of the waveguide and B is the vertical width. So if we now put an assumption that A is more than B, then in that case I can say that FC will be less than FC of this one. So definitely I can say the lowest FC will be when m equals 1, n equals 0. So therefore, of all possible modes, the lowest cutoff frequency will be for the mode TE10. So even if you increase the value of m and n, definitely the value of FC will increase. So the propagation mode with the lowest cutoff frequency is that for TE10. So therefore, we say TE10 is the dominant mode. Dominant mode in a rectangular waveguide, since it has the lowest FC. Since it has the lowest FC, it can pass more frequencies. As you know, for the wave to pass through the waveguide, its frequency must be above a certain cutoff frequency. That is what we proved in the last class. So this is a very important thing. So the dominant mode in case of the rectangular waveguide is the TE10, not TE01. Alright, and definitely TM11 comes later. So that is the way we look at the cutoff frequency. Now, if you recall, we had a very similar discussion pertaining to the parallel plane waveguide also, where we said that TE and TM modes in general can exist, and there the dominant mode was TM0. It was dominant because that mode had a very distinct feature of not having any cutoff frequency whatsoever. That was in case of the parallel plane waveguide. So in that case, we saw it is passing everything from DC to infinite frequency, and that is the TEM mode. TM0 is nothing but the TEM in case of parallel plane waveguide. So the moment we talk of modes which are non-zero and the concept of cutoff frequencies, the medium essentially becomes dispersive. Why? Because different modes will travel with different velocities. We are just going to come back to this in a short time, but that is what it is. So the question now is, can we have a dispersionless kind of propagation or the TM mode of propagation inside the rectangular waveguide? So this is the $1 million question. Is TEM mode of propagation possible inside the rectangular waveguide? Well, TEM propagation means that both Ez is 0 and Hz is also 0. So as far as the general means of analysis that we developed in the last couple of classes is concerned, the moment we have Ez and Hz both as 0, all the transverse waves or the transverse fields will also vanish. And that should not be a major cause of concern, because over there we had developed the analysis technique with the underlying assumption that we suppose that there will be some component always which is longitudinal. Some field component must always be there which is longitudinal. So we never really took TEM into consideration when developing that model. So therefore, those equations where we get the transverse fields as functions of the longitudinal fields cannot be used for this analysis. So therefore, we shall look at this problem a little more qualitatively. So let us draw the waveguide. So it looks something of this kind. So this is the z direction, this is the y, and this is the x. Now what happens here is we do not know whether TEM can exist. That's what is the question that we are asking ourselves. So since we do not know much about how the fields inside may look like because of TEM at this point, let us start with a very brave assumption that TEM exists. So let's assume TEM exists. Very good. Now what does that mean? That means that essentially the wave is propagating along the plus z direction. Alright, that means if the wave is traveling along the z direction, the E and H fields must lie on the transverse plane, that is the cross section of the waveguide, which is nothing but the xy plane. So definitely the E and H fields will lie on this plane. Now comes the interesting part. Let us talk about the H field. What will the H field look like? Now what is happening over here? We have a structure which has two pairs of walls. One pair of wall is over here, which are vertical. The other pair is a horizontal pair. So if a magnetic field has to exist, it must satisfy the boundary condition for all of these surfaces. So therefore, the magnetic field must exist by being tangential to all of these walls. So it can exist something like this, or something like this, something like this, or something like this, as an example. So the H field component must graze the boundary wall, because that is the only way with which it can satisfy the boundary conditions. The H field being normal is not possible, because as per Gauss law of magnetic flux and the boundary conditions, the normal component will die down. Now, suppose this field exists the way we are saying it does. So the question is, the TEM mode is existing, so what will the magnetic field lines look like? So back to the basics, that is Ampere's law. So Ampere's law states that every current carrying conductor will have a magnetic field that will loop around. So because of these four walls, the magnetic field cannot exist outside the conductor, because we just said that the normal component has to be 0. So therefore, the field lines, the H field lines, will look something of this kind. They will be like a closed loop. And the magnetic field lines also have to be closed loop, because their divergence is 0, as you very well know. So let us say something of this kind also is possible. This is what the H field may look like. So if the H field looks like this, then as per Ampere's law, there must be a current element along the z direction, because that's the only way it can satisfy the right hand thumb rule. If there is a current element along the z direction, then if you apply right hand thumb rule, the magnetic field lines will go clockwise. So, well, then what's the problem with that? That means some current element has to exist along the plus z direction. So, some current has to exist along plus z. Now, as per the Maxwell's modification to Ampere's law, the current can be of two types. One is the conduction current density, the other can be the displacement current density. Conduction current density is not possible because although the walls are metallic, the medium inside the waveguide is a dielectric, so therefore J cannot exist. But in the dielectric, definitely we can have some displacement current density. So if the displacement current density is non-zero, this implies that there is some electric field also along the z direction which is non-zero. But what did we say? We said that our initial assumption is that the TEM mode will exist. So whatever is the result we are getting, that is contradicting our initial assumption. So therefore, this discussion is just not possible. So TEM mode cannot exist. This is the answer. End of story. TEM mode cannot exist. So therefore, propagation of waves in a dispersion free manner is still a dream. So that's a really sad story. But without getting too depressed about it, we must ask ourselves, fine, even if the TEM mode cannot exist, even if we cannot make a wave propagate without any cutoff frequency, what is it that we are gaining? We are gaining something very important. We showed that using a single conductor, notice that this is a conductor or a tube made of a single piece of metal. Unlike parallel plane waveguides, which were two different conductors, we are using just one conductor to guide a wave or transfer energy from one end to other end. So therefore, we are kind of trying to stretch the law of nature. And we learned in our circuits course that we need two conductors for current to flow, but no, we can even make the electromagnetic energy flow from one side to the other side using a single conductor only. And that is possible only when the frequency is very high, much above the cutoff frequency. So, that is the way with which this works. So obviously when it is DC, when the signal is DC, it will look as if this is a single conductor. So therefore nothing will pass. But as the frequency increases, the dimensions of the waveguide essentially become comparable to the wavelength of the wave. So therefore, this short circuit does not act like a very good short circuit. And that is the power which has been given to us and that we are utilizing to generate the different modes and transmit the signals. So now let's look at the phase constant of the guided wave traveling along plus z direction. and that is beta, which is, or rather beta square, which is omega square mu epsilon minus h square, and omega square mu epsilon is the beta square of the wave that is entering the waveguide, which will be reflected multiple times and will travel. So therefore I can say beta is under root of omega square mu epsilon minus h square. H square we already know what it is. That is m pi by a the whole square minus n pi by b the whole square. I'm taking the whole minus, therefore we get two minus signs, and this is what beta is. So the phase velocity Vp, that is omega by beta, that is nothing but omega divided by this big expression for beta, which is omega square mu epsilon minus m pi by a the whole square minus n pi by b the whole square. Now if we talk of the group velocity, group means what? The group velocity means the velocity with which the energy of the wave is traveling. One more way to look at this is that if we have a signal which has multiple frequency components, then what is the velocity with which the energy is traveling? In that case, you need to differentiate this equation. So the group velocity in this case will be nothing but, since omega is variable, you will have something like del beta by del omega the whole inverse. So if you differentiate this equation with respect to omega, what you will essentially get is something of this kind. This is the energy, or this is the velocity with which the net energy in the signal will flow. So what you can see is that both group and phase velocities, they are dependent on frequency. So what we can say is that Vg, Vp both, they both depend on omega. So therefore this is a dispersive mode of propagation. There is nothing you can do about it. There is nothing absolutely which you can do about it. So it is like saying, if you have a signal, let us say I have a rectangular waveguide, and I have something like a electromagnetic pulse generator, and this I am trying to feed inside. Now suppose this is a square wave of some frequency, where let us say the f0 is the frequency of the square wave and this is more than f cutoff. So definitely this will pass. But as per Fourier's theorem, a square wave is not just f0. The square wave has multiple frequency components, f0, 3f0, 5f0 and so on, all the odd frequency components. So therefore each of these frequency components will travel with different velocity. And at the end of the waveguide, if you are measuring the signal, you will see that the nature of the square will not remain anymore. So if this is a square wave, this might become something of this kind. Just an example. This is not exactly what it may look like, but something of this kind. So the nature of the wave will be lost. So if you are sending a sine wave, it's fine. But if you are sending anything other than a sine wave, which has multiple frequency components, then definitely you will have some kind of a shape distortion at the output. So what One of the easiest examples in practice for this phenomena is an optical fiber. Even though an optical fiber is not made of metal, it still has the different modes of propagation which we discussed. And if you send a pulse of light, now depending on the nature of the pulse and also how long the optical fiber waveguide is, the output may be a distorted pulse. So this is a very important phenomena, how you can actually pass a signal from one end to the other end of the waveguide with minimum distortion. What is the best possible mode with which you can make it travel? Now these are different things which electromagnetic engineers ask themselves. As far as this particular course is concerned, we shall not be bothered with those applications. Those applications are of a lot of interest to RF and microwave engineers who use different kinds of waveguides. So they have to decide what is the best possible way to make them travel. So with this, we come to the end of the discussion of waveguides. Thank you very much.